Hello everyone, welcome to our differential equation class. In this video we introduce a particular type of second order linear differential equations that are homogeneous and with constant coefficients. First we are going to review the general solution theorem that we discussed in a previous video. Then we are going to use that theorem to find solutions of these differential equations, homogeneous with constant coefficients. And the way we are going to find all the solutions is by guessing fundamental solutions, because these equations are simple enough that we can guess fundamental solutions. Once we have fundamental solutions, this theorem is going to tell us that we have all the solutions of the differential equations, and that is going to be the main result of this video. So that's the plan for today. Let's start with a brief review of the general solution theorem we introduced in a previous video. That theorem says the following. Suppose you have two functions, y1 and y2, and these functions are solutions of the same equation, and where L is a linear second order linear differential operator. So this equation has second order linear differential equations. So the assumption so far is y1 and y2 are solutions of the same second order linear differential equation, and on top of that, suppose that these two functions are not proportional to each other. When that happens, you are done, because this theorem says that every solution of the same equation can be written as a linear combination of these two solutions, y1 and y2. So to find all the solutions to these equations, the only thing we need to do is to find two solutions that they are not proportional to each other. So because of this important property that these two solutions have, these are called fundamental solutions. So fundamental solutions are two solutions of the differential equation that are not proportional to each other. And then this formula over here is called the general solution of the equation. And this result was first found and written by Leonhard Euler around 1739. So what we are going to do now is we are going to use this general solution theorem to find all the solutions to a differential equation of this form in a particular case. In the case that the differential equation or the differential operator has constant coefficients. If the operator has constant coefficients, so the equation is second order linear differential equation homogeneous with constant coefficients, in that case we are going to be able to actually guess fundamental solutions. The equation is so simple that we are going to guess the solutions. And then this theorem is going to tell us, okay, then you have found all the solutions of the equation, again, in the case of homogeneous constant coefficients. So that's the idea. That's how we are going to use this theorem. When the equation doesn't have constant coefficients, when we have variable coefficients, we don't know how to guess. It's too difficult. But it's simple enough in the case of constant coefficients. So let's see how we can guess solutions, fundamental solutions, in the case of constant coefficient equations. So our next topic is then guessing fundamental solutions. And we are going to start with a particular example. Suppose we have this differential equation, this one here, and you see constant coefficients, 5 and 6. And the problem is find all solutions. So what we need to do, according to the previous theorem, is to find two solutions, y1 of t and y2 of t, not proportional to each other. And we are going to guess. So how do we guess? Well, we start guessing, for example, with a constant. We are going to plug in a constant in here for y and see if we can get a solution. If not, we are going to try polynomials, so power functions. If not, we are going to try exponentials, and if that doesn't work, we are going to try trigonometric functions like sine or cosine, and if that doesn't work, well, we don't know. Then we are stuck. So that's how guessing works with simple functions, and if it doesn't work, it does not work. So let's start with the simplest case, y of t equal a constant. Okay, if we put that into the equation, so that's the idea, that goes into the equation. And what do we get? We get the constant second derivative plus 5 constant first derivative plus 6 times the constant equals 0. Of course, this term here is 0 because it's a constant, the derivative is 0, the same here. So we end up with an equation that says 6 times 0 is 0. Of course, we can divide by 6. And the condition we get is that the constant has to be 0. Which, well, we found one solution, which is the trivial solution. Of course, in this equation, if we put 0 here, well, this is going to be 0, and 0 is equal 0 is a solution, but it's the only solution. So we only found that 0 is a solution. Not very interesting, but is something after all. Then let's move on to the next function in complexity. Let's suppose power functions. And I want to try not only with t squared or t cubed, I want to try with all possible power functions. So I put an n here, and I try to find a value of n, of the power, such that y equal t to the n is solution of, this is the equation 1. Okay, so we are going to plug, t to the power n into the equation. So second derivative plus 5 t to the n first derivative plus 6 t to the n, and we are looking for a value of n such that this is 0 for all t, isn't it? So that is what we want to find. Now, this term over here is the same, 6 t to the power n. Now, this term here, we compute the derivative, and if you recall, the derivative is, well, we have the 5 here, the derivative is n t to the power n minus 1. This is the first derivative. The second derivative is going to be the first derivative, and then we compute one more derivative, so we are going to drop that n minus 1. So here we are going to have actually n minus 1 t to the n minus 2. So that's the second derivative. Now we can pull common factor, for example, t to the power n minus 2, and then we are going to have here n minus 1 plus 5n t plus 6 t squared, all equal 0. All right, then we can simplify that t to the power n minus 2, and we end up with an equation that is an equation for n. That's okay, and the equation for n is n minus 1 plus 5 nt plus 6 t squared equals 0. And again, this is for all t. Well, but this equation, because it's for all t, says that suppose you evaluate this equation, if we find, what we are saying here is, if this function t to the power n for any n is solution of the differential equation, then this has to happen for all t. But if we evaluate this equation at t equals 0, we get that that is 0. So at t equals 0, we get n minus 1 has to be 0. And if we evaluate which means that n is equal 0 or n is equal 1. So there are two possibilities. But n equals 0 cannot be, because if n is 0, this coefficient is 0, this coefficient is 0, and we get a contradiction. So the case n equals 0 tells us that 6t squared has to be 0 for all t. That is not happening. And if we put n equal 1, then what we get from here is that 5t plus 6t squared has to be 0 again for all t, which is not happening. So what we conclude from here is that y of t equal t to the power n is not a solution or is not a solution of equation 1 for any n. Any value of n real. So let's say any n real. So this guess does not work. Power functions are not solutions of the differential equation, because we get that only two powers are possible. One power is actually the constant, so we get that is not a solution, and the function y of t equal t when n is equal 1 also is not a solution. Alright, so we failed with the constant, we failed with the power function. Let's keep going down our list and try the exponential. So in this case, we want to try not only with just exponential t or y equal exponential 2t. I want to try with all possible exponentials. So the exponent, I'm gonna keep it arbitrary. I'm gonna call it r, and I'm gonna try all exponential of the form exponential rt. And maybe we see if we can find one value of r that the function exponential of rt is solution of the equation. So we do what we did in the previous case. We plug the exponential into the equation. The equation is a second derivative, so we put exponential rt. We need to compute the second derivative plus 5 exponential rt. We need to compute, this is a t here, we need to compute a first derivative, and then plus 6 exponential of rt. All that has to be 0 again for all t. But what is the derivative of the exponential? The derivative of the exponential is, let me write it here. This term, nothing happens, r of t equals 0. In the previous term, we need to compute the derivative of the exponential, but that drops an r, and then we have exponential rt. So let's write it. This is going to be 5 r exponential rt. And what is the second derivative? Well, the second derivative is the first derivative, so it's r exponential rt, one more derivative, so we are going to drop one more r. So we have here r squared exponential rt. That's the second derivative. Okay. And then we realize we can pull common factor this exponential, and this exponential. We pull it common factor, and we are going to have down here the exponential rt, and it's going to be common factor of r squared plus 5r plus 6, all that equals 0. And this equation looks really good because of the following property. As before, we can cancel the exponential, but then look what equation we get. After the cancelling of the exponential, we get an equation that does not have any t on the equation. It's only an equation for r, and the equation is that r squared plus 5r plus 6 has to be 0. We know how to solve these equations. So it looks like we are going to be able to find values of r after all. So this equation is important, so we are going to give it a name. We are going to call it the characteristic. It's kind of, we are running out of space, so let's move everything to this side. And now we have space, characteristic equation, and we know how to solve it. Recall that whenever you have let's put it in the different color. Recall, suppose we have to find the values of r, solutions of an equation, a general equation of the form a r squared plus b r plus c equals 0. Then there is a formula for r which gives us two solutions, and these are 1 over 2a, and then we have minus b plus minus the square root of b squared minus 4ac. This is the very old formula to find the solutions of the roots of a quadratic equation. So recall that. If we use that formula in our problem, we are going to get that r plus minus is going to be given by 1 over 2, a is 1, then we are going to have negative 5, then plus minus square root of 25 minus 4 times 6. And maybe it's a good idea to write it down as 5 squared. Alright, that is the formula, and then we can actually compute the roots because the numbers are simple. And this is going to be 25 minus 24. And here we can continue, and this is the same as 1/2 negative 5 plus minus 1. So we get two solutions. The solution r plus is going to be, when we have the plus here, so it's going to be negative 4 divided by 2, so it's going to be negative 2. And then we have the solution r minus, which is when we subtract, so it's negative 6 divided by 2 is negative 3. So we actually found two exponents that when we put these exponents in the exponentials, we are going to get solutions. So what that says is that we found two solutions. The solution that we can call y plus, which is exponential of negative 2t, and then the solution that we can call y minus, which is exponential of negative 3t. These are solutions of the differential equation because of the calculation we did before. You can plug these functions into the equation and you're going to see that they are solutions, and they are actually not perpendicular to each other. So it's very easy to see there are two different exponentials, so y plus is not proportional to y minus. So that says that these are fundamental solutions. Of equation 1. Okay, but the theorem says that we have found all the solutions. So now all the solutions of the equation are linear combinations, and we can call the coefficient c plus exponential negative 2t plus c minus exponential negative 3t. These are all the solutions of the differential equation. So this is then the general solution of equation 1. And we've done it. See here, you see C plus and C minus are arbitrary constant. We say that by saying they belong to the real numbers and no condition. This symbol here is the symbol belong to. And we are done. That's the calculation. Because the equation is so simple, constant coefficients, homogeneous, we were able to just guess fundamental solutions, and because of that we got all the solutions of this particular example. Now the calculation we have done in this theorem is essentially the main part of the proof of the following result. In other words, we can summarize the calculation in the previous examples in the following theorem. Before the theorem, we need an important definition, and the definition is the differential equation y double prime constant coefficient a1 times y prime constant coefficient a0 y equals 0. Let's call that the linear differential operator, and that the homogeneous equation with constant coefficients. That equation, where a1 and a0 are constant, has what is called a characteristic equation, and the characteristic equation is replace the second derivative by r squared, the first derivative by r, and use the same constants a1 and a0, and this is what is called the characteristic equation of the original differential equation, and this here is the characteristic polynomial. Recall how we obtained in the example this equation. What we did is we plug the y of t equal an arbitrary exponential of rt. We put that into the equation, and then because of that we got the characteristic equation. With that definition, now we can state the main result, and the main result is, given a second order linear differential equation homogeneous with constant coefficients like this, and given that equation, let's call r plus and r minus the roots, so the solutions of this equation, the roots of the polynomial or the solutions of this equation. Okay. Then we have actually two cases. Actually, the first case is the case we covered in the previous example, and is the following. Suppose that the roots are different. These roots here are different. Real or complex, doesn't matter, but they are different numbers, like in our example, -2 and -3. Then the fundamental solutions of the differential equation are the function that we found in the previous example, exponential first root times t, exponential second root times t. But we know that the characteristic equation may have a repeat root. What happens in that case? In that case, suppose we have a root, r plus, and r minus, which are the same. Let's call it r0. Then, of course, we have one fundamental solution, but what is the other? We are going to figure that out in a minute. Once we figure out what is the second solution in this case, we are going to find the function here that we are going to write down here, and then this is going to be our main result for this video. But let's prove part A. But the proof is essentially the calculation we did in the previous example, so we need to repeat that calculation, proof. What did we do in the previous example? So we are talking about part A. Let's put it a little bit down here. What did we do in the previous example? when we have a particular equation. In the previous example, we have the equation with 5 and 6. What did we do in that case? Well, we look for solutions that they are exponentials. So this is what we are going to do now. Now that we have arbitrary coefficients, y double prime plus a1 y prime plus a0 y equals 0, we are going to do the same as we did in the example. We are going to look for solutions that they are exponential of RT. And when we put that in here, what is going to happen? Well, we are going to have r squared here, exponential, plus a1, r exponential, plus a0 exponential. So exponential is going to be a common factor here, and all that has to be equal 0. And then we can do the cancellation we did before, and from here we end up in the characteristic equation. So from here we end up that r has to be solution of this equation, r squared plus a1 r. So we are running out of space, so let's put it here. We end up that r has to be solution of r squared plus a1r plus a0 equals 0, which is the characteristic equation. And then we say that by assumption, this equation has two solutions, r plus and r minus. By assumption, these two solutions are actually different. Well, then that's it. Because then we know that y plus equal exponential r plus t and y minus equal exponential r minus of t. These are going to be fundamental solutions of the equation, and let's call it of 1. And that's all. So the same calculation we did with 5 and 6 works in general if we assume that whatever equation we get for r, this is our assumption, has different roots, which is what we are assuming here in that case. So an example of this case is the example we solved before, but now we don't need to guess too many different functions. Now we know that exponentials work. So suppose now we have a new problem, which is find the solution of the initial value problem given by this equation. You see we have different coefficients now and two initial conditions. So how do we solve this problem now that we know the previous theorem solution? So now it's very simple. What we do to solve this problem is we write the equation we work with, y double prime plus 3 y prime minus 4y equals 0, and now we know that exponentials work. So we put in here an exponential. The only thing we need to do is find the exponent, and that is going to give us, when we put the exponential in there, it's going to give us an equation for the exponent, r squared plus 3r minus 4 equals 0. Because recall, what is going to happen is we are going to have an exponential common factor, and we are going to be able to cancel it because we have 0 on the other side. So from here we use the formula for the roots, and we end up that r plus minus are going to be equal 1/2, then negative 3 plus minus square root of 3 squared, which is 9, minus, and this minus is plus, so well, let's leave it like this, minus 4 times negative 4. Let's write down the equation a little bit more clear. So this is equal 1/2 negative 3 plus minus the square root of 9 minus minus and minus is plus 16. So it's 25. So we have 1/2 negative 3 plus minus square root of 25. Then we have easy numbers. And then we have 1/2 negative 3 plus minus 5. And we get two solutions. When we choose the plus, we have a 2, so r plus divided by 2 is 1. And then we have the r minus, which is 8. Negative 8 divided by 2 is negative 4. So now what this calculation says is that we have fundamental solutions y plus of t equal exponential t, and y minus of t equal exponential negative 4t. And with that, we have the general solution, which is an arbitrary constant, let's say c plus exponential t plus c minus exponential negative 4t. So we have found all solutions of that differential equation because we needed to find only two, not proportional, and we did. So then this is the general solution of the equation. And now we need to find the specific solution that satisfies these initial conditions. So now we have initial conditions. And the initial conditions are that y at 0 is 2, and then the derivative is 3. And we want the function that has derivative 3. Okay, the first condition is easy to implement because 2 has to be equal the function at 0. But I have the function here, so I'm going to put 0, 0, and 0. This is going to be 1, this is going to be 1, and I'm going to have that this is equal c plus c minus. So one equation for the coefficients is that c plus c minus is equal to. Okay, but that's not enough to find the coefficients. We need a second equation, but our second initial condition involves the derivative, so we need to compute the derivative first. So what is the derivative? Y prime of t is c plus exponential t minus 4c minus exponential negative 4t. Alright, now we can put the initial condition, which is 3, has to be equal y prime at 0. But I have what is y prime, I plug 0 here. Again, this is going to be 1, this is going to be 1, and we are going to have this equation now. So this is going to be equal c plus minus 4 c minus. So here is a second equation that the coefficients have to satisfy. C plus minus 4c minus has to be equal 3. And now we have two equations for two unknowns. So we solve it. And how do we solve it? For example, we substitute from here one of the variables, for example c plus, in terms of the other, and we put it in here. So from the first equation, we get, let's do it here, we get that c plus is equal 2 minus c minus, and we put that into the second equation. So we have 2 minus c minus minus 4c minus equal 3, which is the same as saying that we have 2 minus 4 is negative 2, minus c minus, we have positive 2, and then we have here negative c minus, and here we have a negative 4, so it's negative 5. Negative 5 of this c minus equal 3. So, which means that negative 5 c minus has to be equal 1, and from here we get that c minus is negative 1/5. Alright, if we know that c minus is negative 1/5, we go to the first equation. So we put now that in here, and we get C plus. And C plus is going to be 2 minus negative 1/5. And this is equal, how many fifths? Is 10/5 plus 1/5. So we have found that C plus is actually 11/5. And that's it. Our solution, y of t, I'm running out of space, but it's going to be just enough, is C plus, which is 11/5 exponential t minus 1/5 exponential negative 40. And that is that should be the solution of our initial value problem. And this is how you solve this problem using the previous theorem. Just find the roots, and so plug an exponential, get the characteristic equation, find the roots, then you have your two fundamental solutions, that means all the solutions, and then impose the initial conditions to get the constant. The initial conditions fix the constants like we did in this problem. Now we need to continue with the second part of the theorem. Recall, when the roots are different, we know what to do. What happens when the roots are repeated, the roots of the characteristic equation? We already have one solution, but with that root, what is the second solution? So to answer that question, I'm gonna write here a proof, but so it's the continuation, but we need to find the second solution. So proof, and is continued from above. And let's see what we can do. So we are in case B. Case B is we are trying to find the solution of this equation, y double prime plus a1 y prime plus a0 y equals 0. So as usual, we plug an exponential in there. This is our guess for a solution. We know this exponential usually work, RT, and we are gonna get an equation of the form exponential RT, and then we are gonna have r squared plus a1r plus a0 equals 0, and we cancel this exponential and we get the characteristic equation for the exponent, r squared a1r plus a0 equals 0. Okay, that's the characteristic equation. What are our assumptions now? In part B, we assume that we have a repeated root. So r plus is equal r minus, and let's call either of these two, so the same, r0. So actually we have two assumptions here. One is that r0 is a root, so r0 satisfies the equation. r0 squared plus r0 is a number such that r0 squared plus a1 r0 plus a0 is 0. That's the first condition for r0. But we have a second assumption, which is r0 is the only root. What that means? Well, if we use the formulas for the roots, r0 is 1/2 the negative a1 plus or minus a1 squared minus 4a0. But we have only one root, so what that means is this part here inside the square root has to be 0. So the coefficients have to be such that that happens, and when that happens, the formula for R0 is negative A1 over 2. We can rewrite this formula in a simpler way. We multiply everything by 2, and we move the A1 to the other side, and this formula can be written now as okay, let's do it down here so we have a little bit more space. This formula can be written as 2 R0 plus A1 has to be equal 0. This is the condition that R0 is the only root. So R0 satisfies both equations. This equation because it's a root, this equation because it's the only root. Alright, so now what do we do? Well, let's go back to our equation. The equation is y double prime plus a1 y prime plus a0 y equals 0, and we have one solution. One solution is, because we have R0, one solution is, let's call it y1, which is exponential that R0 times t. We know that. So now we need to find a second solution. So what is the idea here? So idea, we don't have a second solution y2, so what is the idea to find? Find y2 of t not proportional to y1. How do we find that function? Well, the idea is, let's look for, or let's write here, let's write the solution we are looking for, y2, as some function of t times the first solution, the solution we already have. Put that into the equation. So the idea is put that into the equation y double prime plus a1 y double prime single prime plus a0 y2 equals 0. Put that into here and use that this is use that this function is a solution to get from here an equation for v of t. Hopefully the equation for v of t is simpler than the equation for y2 because y1 is a solution. So the hope is equation for v of t is simpler than equation, let's call here equation 2, because this is just a hope. There is no guarantee that is going to happen, because y1 of t is already a solution of equation 2. So that's the main idea. Now we need to do the calculations. We need to let's mark here that this is the important step. We need to put that into the equation, but to put that function into the equation, we need to compute y2 prime. What is y2 prime? Well, it's v times, let's write down what the exponential is what y1 is an exponential r0t. we need to compute the derivative of that. So let's do it. This is product rule. So this is going to be v prime exponential r0t plus r0 v exponential r0t. We see from here we can take common factor the exponential r0t is a nice common factor of v prime plus r0v. Alright, this is y2 prime. We are going to need this expression. Recall the when we plug the exponential, y2 is just v exponential r0t. So we have that. We have the first derivative. Now we can use this formula here to compute the second derivative. It's going to be longer, so let's do it over here. y2 double prime is going to be, let's use this expression, is going to be the derivative here plus the derivative here. So let's write that down. It's going to be v prime exponential r0t prime plus r0. I can take it outside of the derivative because it's a constant, exponential r0t prime. So two product rules now. So here we have v double prime exponential r0t plus r0 v prime exponential r0t. This is from the first term. The second term, the derivative on v gives us an r0 v prime exponential r0t, and then we have a derivative of the exponential which is going to drop another r0, so r0 squared v exponential r0t. Complicated, but not that much, because we can pull common factor and exponential r0t, and notice that this term here is exactly the same as this term here, so we can pull a 2. So we have v double prime, then we have 2 r0 v prime, and then we have r0 square v. So this is our second derivative. And now we put everything into the equation, and we see what equation we have for v. The equation is then the second derivative, which is going to be exponential r0t multiplying the second derivative, which is v double prime plus 2 r0 v prime. So now I'm writing this equation here. So maybe it's a good idea to copy this equation. Copy. So now what we are doing is, let's move this down a little bit. We are computing this equation, but with the second derivatives and first derivative we found. So the second derivative still has an r0 squared v, and then plus a1 times the first derivative, which we have it up there. It also has an exponential, which is already here, so we only need to write v prime plus r0v, and then plus the function times the coefficient, but this exponential is already there, so we have a0 v. All that equals 0. Of course, the exponential can go away, and now we put terms together. We have the second derivative for v. Then what do we have? Let's start highlighting terms. We have all the terms that have v prime, which is this term with a plus sign. Then we have this term that is multiplied by a1 and nothing else. So we have v prime that multiplies 2 r0 plus a1. And then we have the terms that have v, and this is going to be that term multiplied by a1 and this term. So v can be pulled common factor, and then it's going to be v multiplied by r squared plus a1 r0 plus a0, and all that equals 0. So this is the equation for v. It doesn't look simpler than the equation for y2, but actually it is, because recall, I forgot here, this is an r0. And recall, r0 is a root, which means this part is 0. Is this hypothesis on r0. Because it's a root, that term has to be 0. But notice that this term also is 0. Why? Because r0 is the only root. It's repeated. So actually, the equation for v is simpler. It's just v double prime equals 0. That's the equation for v. So yes, it was simpler. And we know what the solutions are. The solutions are v of t, an arbitrary constant multiplied by t plus an arbitrary other constant. And with v, we have all the solutions for y2. y2 of t is c t plus d exponential r0t. These are all possible solutions for y2. Now we are interested in, recall what was y1. y1 is the exponential alone, exponential r0t. So here c, d are arbitrary constants. So for example, what happens if we choose c equals 0 and d different from 0? Well, then y2 is going to be just d times the exponential. So it's going to be proportional to the first solution. We are not interested in those solutions. So actually we are interested in choosing d equals 0, because this is the part of the y2 that is proportional to y1. We don't care about that. We care about that part. And let's say c equal 1 to choose the simplest solution. And here we have y2 of t is t exponential r0t. That is our second solution that is not proportional to the first, because this is not a proportionality factor. This is a function that changes in time. It's not a constant. So y1 and y2. And these are fundamental solutions. So now we can go back all the way to the theorem and write what goes here. What goes there is t exponential r0t. And with that, we have, now is a proof, and we have proven the theorem by finding a second solution not proportional to the first one. Let's finish this video with one last example, and this is our last example. Suppose we have this spring mass system with all these parameters. Find all the possible movement for the system, and then find the solution with these initial conditions. The velocity here is negative, which means, recall, positive is downward, so a negative velocity means at initial time the velocity is upwards. Okay, so now we don't need to do all the calculations in the theorem to solve this problem. We can use the theorem. So what is the equation for this spring? It's Newton's equation of motion. We recall the general equation is mass, acceleration, and then we have here the dissipation coefficient, the damping coefficient times the velocity, plus the spring constant times the displacement equals 0. We have values for those parameters, so we have our equation which has mass 1, then 6 for the dissipation constant or the damping constant, and 9 for the spring constant. So how do we solve this equation with constant coefficient homogeneous? Well, now we know. We guess that the solution is going to be an exponential RT. We put it in there. We get the characteristic equation r squared plus 6r plus 9 equals 0. We solve it, and the roots are going to be 1/2 -6 plus minus square root of 36 minus 36. So we are in the case that we are going to have one single root. This implies that r plus is equal r minus, and both they are equal to -3. So this is r0 from the previous calculation. R0 is -3. So we don't need to repeat the calculation in the theorem. Now we know that one solution is going to be exponential -3t, but the other solution is going to be t, exponential -t. So these are our fundamental solutions. Now that we have the fundamental solutions, we can write the general solution, y of t, which is going to be c1 exponential -3t, and then c2, an arbitrary constant c2, t exponential -3t. These are all the solutions to the problem. And now we have initial conditions. What are the initial conditions? Y at 0 is equal to, and y prime at 0 is equal -2. So we can apply the first condition. 2 has to be our solution that we already have at 0. But now we plug 0 here. We plug 0 up, but look, we have a 0 here. So c2 disappears. This is 1, and we have only c1. So it's c1 plus 0. So we already know that c1 is 2. Okay, now for the second condition, we need a derivative. So let's compute the derivative. We can compute the derivative replacing c1 or not. It doesn't matter. Let's do it without replacing the derivative, replacing the value. So we have to derivate the exponential, so it's -3. c1, which we already have, exponential -3t. And here, well, here we have a product rule, because we have a product of two functions. So here we are going to have c2. When we derivate t, we get only the exponential. And when we derivate the exponential, we keep the t, and we have a -3 exponential -3t. All right, no need to simplify, is enough. So now the condition is that -2 has to be equal this derivative at 0, but if we put 0 here, we get a 1. If we put 0 here, we get a 1, and if we put 0 here, because of that, we get a 0. So this is going to be -3 c1 plus c2 multiplied by 1 plus 0. But we already know what c1 is. So we have -2 is equal 2 times -3 is -6 plus c2. So from here we get what c2 is. We move it to the other side, and it's going to be plus 4. 6 goes as +6. So these are our two constants, 2 and 4, and we have found the solution of our problem. Y of t is, by the way, we can pull common factor the exponential, and this is going to be 2, this is going to be 4, so we can pull a 2 common factor. So we have 2 exponential -3t, and now we have 1 in the first term plus 2t. And this is a nicer way to write our solution for this initial value problem. And this is how we use this theorem, general theorem, guessing fundamental solutions, and then we can find solutions to initial value problem in the two cases, repeated root or different roots. So that's all for this video. This is a good place to stop. See you guys in the next video.